Since elementary school, we've been taught a simple, unquestioned fact. Plants are green because chlorophyll reflects green light. But that familiar textbook answer hides a much deeper and almost baffling paradox. Why green? Of all the colors pouring down from the sun, why would plants reject the very color our star produces almost intensely? The sun's energy output peaks somewhere in the green to yellow region of the visible spectrum, making green one of the most abundant forms of sunlight reaching Earth. Logically, plants should have evolved to harvest this enormous reservoir of energy. Instead, they mostly let it go. To understand why, we have to descend into the quantum architecture of life. At the center of every chlorophyll molecule sits a magnesium ion surrounded by a large ring of carbon and nitrogen atoms called the porphyrin ring. Together, they form an exquisitely tuned molecule antenna that captures light. But chlorophyll doesn't observe every color equally. Its electronic structure naturally creates two strong absorption bands, one in the blue region around 430 nanometers and another in the red region around 660 nanometers. When photons of these wavelengths strike the molecule, they efficiently excite electrons, initiating the chain of reactions that powers photosynthesis. Green wavelengths, however, fall between these two absorption peaks. They are much less likely to be observed, so a large fraction is reflected or transmitted instead. Plants didn't deliberately reject green light. They inherited the quantum properties of the molecules evolution had available. There's an intriguing hypothesis about this, though it's still speculative. It suggests this constraint goes back billions of years to the primeval oceans. Ancient purple and reddish microbes may have dominated the shallow waters back then. Unlike plants, they used retinol-based pigments instead of chlorophyll, and they were efficient at absorbing green light for their own energy needs. If that's true, the ancestors of modern plants were forced to adapt. They had to make do with the leftovers. The blue and red light those microbes didn't want. It's a compelling story, but it's far from settled science. Chlorophyll's particular chemistry may simply be what worked best, regardless of who came before. Yet, what first appears to be a limitation turns out to be an extraordinary advantage. Because the upper leaves absorb blue and red light so efficiently, the light that travels deepest into a forest canopy is increasingly green. Ironically, the color chlorophyll uses least is the color that penetrates farthest. The rejected light becomes a lifeline. Down on the dim forest floor, where most of the premium red and blue light has already been claimed by the canopy above, shade-tolerant plants and mosses live almost entirely on filtered green light. Because a single chlorophyll molecule struggles to catch it, these plants compensate with density, wide, flat leaves, and tissues packed with chloroplast, forming a net fine enough that even elusive green photons can't escape. It's a slow, patient way to live, lowering metabolism, surviving on a tight energy budget, and turning the canopy's leftovers into a daily meal. For decades, science underestimated green light's role because researchers only studied isolated chlorophyll in liquid test tubes. There, green light does pass straight through, but a living leaf is in a test tube is a three-dimensional architectural marvel. When blue and red photons strike a sunlit leaf, they are absorbed so aggressively at the surface that the top layer of cells quickly hits what biologists call light saturation. They max out their capacity and waste any excess energy as heat. This is where green light steps in. Because green photons are absorbed less intensely, they bypass those oversaturated surface cells and travel deep into the leaf's interior. There, they bend and scatter off transparent cell walls and fluid pockets bouncing around like a ball in a pinball machine. This pinball effect multiplies green light's travel path many times over, letting it reach the hungry chloroplast deep in the lower tissues that red and blue light never touch. Within every leaf, then, a quiet division of labor emerges. The sunlit surface harvests the premium blue and red photons. The shaded cells deeper within live off the green light filtering through. The energy rejected by one layer becomes the resource that sustains the next. Evolution didn't discover the perfect solar panel. Instead, it discovered one that worked remarkably well and then built an entire ecosystem around its limitations. The vibrant green we see when you look at a forest is not simply the color plants fail to use. It is the color that travels. It is the light that threads its way through countless layers of leaves, quietly sustaining an entire hidden world beneath the canopy. Nature rarely wastes anything. Again and again, what appears to be a flaw becomes an opportunity. What seems like inefficiency becomes cooperation. The forest does not compete only for sunlight. In a subtle but profound way, it also shares it. Perhaps that is the hidden wisdom whispered by the color green. Thanks for watching. If you found this video helpful, give it a thumbs up and don't forget to subscribe to the channel.